In our single input model of Chapter 11, we said it was often most realistic to assume that the production frontier initially becomes steeper and steeper, but eventually becomes shallower and shallower. Another way of putting it at the time was to say that the marginal product of labor was initially increasing and eventually diminishing. We can translate that intuition to the two-input case by saying that it might be most realistic to assume that along any ray from the origin, the slice of the production frontier initially becomes steeper and steeper and eventually becomes shallower and shallower. Now, however, we are varying both labor and capital along that ray from the origin, and so what we're really saying is that the production technology has initially increasing returns to scale, which eventually turn to decreasing returns to scale. We'll assume such a production technology here and see what it implies for the cost curve as well as the firm's supply curve. We then begin with the isoquant for 10 units of output and an input bundle A that uses 2.5 hours of labor and 5 units of capital to reach 10 units of output. We then double that input bundle to get to 5 hours of labor and 10 units of capital, and then keep increasing the input bundle by the same increment of 2.5 hours of labor and 5 units of capital. We therefore plot out a ray from the origin that contains different input bundles, and then draw the isoquants that pass through these input bundles. In order for the underlying production technology to then have the feature of initially increasing returns to scale that eventually becomes decreasing returns to scale, it has to be that initially output increases at an increasing rate as we move from A to B to C, but eventually output increases at a decreasing rate as we move from D to E to F. So, in going from A to B, output increases by 30. Going from B to C, it increases by 60. Then from C to D, it only increases by 40. From D to E, only by 20. And from E to F, only by 10. We therefore see the initially increasing returns to scale turn to decreasing returns to scale along this ray from the origin. If the wage rate is $20 per hour and the rental rate is $10 per unit of capital, we can then produce 10 units of output using the input bundle A at a cost of 5 times $10 plus 2.5 times $20. The slope of the isocosts will be equal to -2 under this wage and rental rate, and if the technical rate of substitution at input bundle A is also equal to -2, then bundle A would in fact be the least cost way of producing 10 units of output. Therefore, we have one point on our cost curve. 10 units of output cost $100 to produce in the least cost way. Now suppose that the underlying production technology is homothetic, which means the technical rate of substitution doesn't change along any ray from the origin. If input bundle A is then the least cost way of reaching the isoquant for 10 units of output, B, C, D, E, and F will be the least cost input bundles for reaching their respective isoquants. We can therefore calculate the cost of producing each of these levels of output by doing the same thing we did to calculate the cost of producing 10 units of output. We can then connect these points, which represent the least cost ways of producing different levels of output, and estimate the shape for the cost curve. Notice that the shape is such that it initially starts steep and becomes shallower and shallower, but eventually becomes steeper and steeper. That's exactly the inverse of the shape that we've assumed for the production frontier along the ray from the origin in panel A. The production frontier along that ray started shallow and initially became steeper, and then eventually became shallower. But both of these shapes tell us exactly the same thing. They tell us that initially it becomes easier and easier to produce, which in turn means it becomes less and less costly to produce additional increments of output, but eventually it becomes harder and harder to produce, which means that costs will eventually increase at a faster and faster rate. In Chapter 11 we showed that the cost curve has the inverse shape of the production frontier, and here again we show that the cost curve has the inverse shape of the slice of the production frontier along which the cost minimizing input bundles lie. From the information in panel B, we can now derive the average and marginal cost curves. For the average cost curve, we can start with point A prime, where we know that we can produce 10 units of output with $100. In other words, at A prime, the average cost is 100 divided by 10. That then gives us the first point on our average cost curve, where for 10 units of output, the average cost is $10. We can then repeat the same process for each of the total cost points in panel B, each time taking the amount on the vertical axis and dividing by the corresponding output level on the horizontal axis. We therefore get one average cost estimate for each output level that we've considered. Notice that what we're doing is no different than what we did in getting from a total cost curve to an average cost curve in Chapter 11. The only complication that arises when we have multiple inputs arises in determining what the cost curve is, but once we have a cost curve like the one in panel B, we can proceed exactly as we did in Chapter 11. Connecting these points, we get our estimate of the shape of the average cost curve. This shape arises from the shape of the cost curve, which in turn arises from the shape of the production frontier along the ray from the origin on which all the cost minimizing bundles lie. Therefore, each of these curves contains the same information. Each tells us that initially it gets easier and easier to produce, but eventually it gets harder and harder to produce. And that emerges from our assumption that initially we have increasing returns to scale, but as production increases, that turns to decreasing returns to scale. The marginal cost at each output level is simply the slope of the cost curve at that output level. It also has a U-shape, and for reasons we've talked about before, it begins at roughly where the average cost curve begins, lies below the average cost curve while the average cost is falling, crosses the average cost curve at its lowest point, and then rises above the average cost curve when the average cost is increasing. The firm's supply curve is then equal to the segment of the marginal cost curve that lies above average cost and goes to 0 for any price that lies below the lowest point of the average cost curve. The reason for this is exactly identical to the reasoning developed in graph 11.11 of Chapter 11. This emphasizes again what we've emphasized a number of times. The complexity that's introduced by having multiple inputs rather than just a single input is in determining the shape of the cost curve. Once we have the cost curve, there's no difference in how we proceed toward the supply curve via the average and marginal cost curves. The average and marginal cost curves just arise from the cost curve, and the supply curve is just the marginal cost curve above the average cost curve. What we've done here is then what we did in Chapter 11 as we developed the two-step profit maximization method. The first step involves deriving the cost curve. The cost curve tells us the least cost way of producing different levels of output. Once we have the cost curve, we can then think about revenues by thinking about how much we'll supply at different prices. Instead of thinking about profit maximization as a one-step process in the complicated graph of 12.1, we can therefore instead use the two-step method developed here.